Hi there, welcome to another video on my Zilog Z8000 Clover computer. Called the Clover computer because it has 4 pedals like a 4-leaf clover. Somewhat of an accident of design. I had originally intended them to stack, but it turned out it was more convenient to let them all sit flat on the table, so I invented this 4-board motherboard to go in the middle so the whole thing sit flat and be easily worked on. This is the second video in this series. If you have not watched the first video, I suggest you go back and watch that one first, because I will not be recovering the parts that I covered in that video. In that video, there were only 3 boards. There was the memory board, display board, and the CPU board, these bottom 3, as well as the middle piece. There was not this top board. So this top board is going to be new for this video, and it is a CompactFlash and Floppy adapter so that we have some real storage to go with this. I'll also be talking about a couple more boards in this, including a speech synthesizer board. Always do a speech synthesizer with my vintage projects. And another board that will be a bus supervisor that allows you to control this thing from a Raspberry Pi. Was very helpful in software development. So at the tail end of the last video, there were a few bugs. I could not get Ed, the editor, to work, or I couldn't get ZCC, the compiler, to work. The good news is I fixed those problems. Everything on this board is now working properly. And the problem happened to be a simple bug with memory segmentation. So CPM 8000 has 2 different types of programs it can load. Can load a combined instruction data program where instructions and data are in the same memory space together, or it can load a separate instruction and data where you have data is segmented away from the instructions, and you can access them and they will automatically go to different parts of RAM. That allows a program that is kind of only 64K aware, it doesn't understand segmentation, to have 64K of data and 64K of instructions. And it turns out that I messed up the memory regions for the split ID, and those were the binaries that wouldn't work. So as soon as I corrected my bug, I fixed CPM 8000 so that it could put the instructions in the right spot in memory. All those binaries that didn't work started working again. So that's the good news. Is this stuff is up on GitHub. The ROMs are there, the PLDs are there, everything you need to get this thing up and running is there. And it's debugged and it's working with a reasonable variety of software. Now, several people have asked me, are you going to make these boards available? Because sometimes you sell boards on eBay. Unfortunately, I've decided I don't really have the time. This project is just complex enough. There's like 8 boards now total. So what I'm going to do is to put all of the Gerber files for these up on my GitHub repo. So that if you want to build one of these, you can just take the Gerber file, you can send it to a place like JLC PCB or the fabricator of your choice. You can order a 5-pack of boards, and you'll have enough to build yourself several Clover computers out of it. Now, it would be nice if I could get a little bit of reimbursement for my efforts. Selling PC boards is one of the ways I'm able to support this hobby. But in lieu of that, just subscribe to my YouTube channel, post, to your friends about the YouTube channel, try to build some more support, and the more people we get, the more advertising revenue, and that does kind of pay for a tiny portion of my development expenses. I might also put a donation link up someplace, if people do want to donate via PayPal or such. But really, I'd rather these boards get in people's hands so that they can start building them. So if you want to build them, order them, get them from a place like JLC PCB, get some for yourself and your friends, whatever you want to do, and build yourself a Zilog Z8000 computer. Okay, here is the CompactFlash and Floppy board. So I think it's relatively straightforward. Over here we have the CompactFlash dominated by the CompactFlash socket, as well as a 40-pin IDE header in case you don't want to do the surface mount socket. Can use either one, but not both. Now, you could actually hook that up directly to the data bus, and some designs do. Back when I did one of my projects, like an XT IDE, I had some CompactFlash cards that would interfere with the data bus. They would pull the bus down. If the card was installed, the thing would become unreliable. So ever since then, I've started putting buffers in so that we only connect the CompactFlash socket when we're actually reading or writing the flash, and it cannot interfere with any of the other peripherals in the computer. So that's this buffer. There's another buffer here for the upper 8 bits. This is a 16-bit computer
Right now, the BIOS does not use the upper 8 bits. We run in the 8-bit mode. So you could probably leave this one out, save a few pennies. Just plain ordinary 74 HCT 245s. There's some resistors for pull-ups and stuff. This is all, you'll see the standard stuff here on RC 2014s and stuff like that. Over here is the floppy controller. Now I think this is a design I borrowed a few times from Sergey's Zeta 2 computer. So it's got a WD37C65 hooked up to a 40 pin, not a 40 pin, hooked up to a 34 pin PC floppy connector. It needs its own crystal, its own 16 megahertz. It needs a few pull-ups over here. And then we need to do some I/O address decoding for it. So I've got an ATF16V8 programmable logic device that will take and put this at the right address. There's actually 3 different chip selects. There's a chip select for the controller, one for the DOR operations register maybe, and the DCR configuration register. And then there's also some logic to trigger DAC at the right time. So it's actually 4 different sort of addresses at play in here to make this controller work. It's a bit of work. It's always a bit of work to get this thing programmed properly. So I spent a little bit of time over the weekend getting the floppy driver working. But I've used this chip in several projects. It's easy enough.
Okay, here is the CompactFlash and floppy board. So we've got the CompactFlash card. It goes in this socket right here. If you don't feel comfortable soldering the surface mount socket, you might want a hot air iron or something like that. Then you can actually use this header here, this 40-pin header, and then you can buy, like on Amazon or eBay, little adapters that will adapt a 40-pin IDE header to a CompactFlash socket. So that's another way to go. I like to build the sockets directly onto my board. It's not that hard to do the surface mount solder. Now down here are the two 74 HCT 245 buffers. Probably only one of them is needed because we're operating CompactFlash in 8-bit mode anyway. Super simple to interface CompactFlash card. That's why every retro computer project has CompactFlash. Over here we've got the floppy controller, a WD37C65 chip, which I have used in several RC 2014 projects, as well as using in a Raspberry Pi project that was quite popular. That chip is here. I did use the PLD right there for it to do its address decode and a few other things like that. There's its pull-up resistor and its crystal. And it has a 34-pin header for your floppy cable to plug in. Some jumpers for some various options that we don't really need there. Now, this did get a little bit close, these two connectors, and I actually had to snip a little bit of the plastic off this shrouded header to get it to fit next to the CompactFlash. I might try to see if I can move something a little bit on the next respin of the board so they're not so tight.
Now the next board I have, I call it a bus supervisor. So I've been doing these ever since RC 2014. And what this is a Raspberry Pi that can take control of the bus and do things with memory. And why is this useful? Well, if you're a software developer, it's really useful to be able to read and write the memory from outside of the computer. So it's kind of like an emulation, like an in-circuit emulator type approach, rather than having to sit down every time you change the BIOS, having to burn a new flash ROM and install a new flash ROM. In the olden days, you actually had to UV erase your EPROMs. It was a very labor-intensive process. You can actually just write main memory. So that's what's really convenient about this thing. So we have a Raspberry Pi. It interfaces through some buffers. So 74 LVC 245Ns. There's 3 of those hooked up to the data bus, as well as some of the address and memory read and write lines. And those things can actually do level shifting. So this is nicely level shifted. So the 3.3 volt Pi gets along well with the 5 volt Z8000. Now there wasn't enough IOs on the Pi for me to do all of the IOs that I needed to do. So there's a couple of MCP 23017 I2C expanders. Now those things are a little bit slow, so you want to do most of your work with the direct buffering. But these here are hooked up to the entire address bus, the chip selects, as well as the bus request and bus ACK. So the way this whole thing works is the Pi asserts bus request. Now the Z8000 will finish what it's doing in an orderly manner, complete its current CPU cycle, and then it will turn over the bus and assert the bus ACK. So when you see bus ACK comes up, your Raspberry Pi can take over. You switch on these buffers, taking control of the data bus, the address bus, and the read-write chip selects, and then you can just start doing memory operations. So you can go in and you can completely write the static RAM. You could probably program the flash chips if you wanted to. You could probably even operate peripherals. For me, I just use it to alter the RAM. So you can read and write RAM with this. The other thing that's really handy is I built into this project, into the supervisor, I built a simulated disk drive. So CPM, when it needs to read a sector, it just writes something to RAM, says, hey, I need this sector filled. And the Raspberry Pi comes along, it's looking at RAM, says, the host computer wants that sector filled, let me go fill it. And then, the Z8000, CPM 8000 can take off again with its sector filled. And then writing stuff goes in the reverse direction. So you can have a simulated shared storage device, and you can, just copy files from your Linux PC into this super disk, and they will appear in the CPM computer. So very efficient sharing of files, an easy way to do software development.
Here is the bus supervisor board. So we have the Raspberry Pi Zero W mounted upside down. It's got its little SD card there. You can power it from the power jack there, as well as power it from a barrel jack here, which I haven't even bothered to populate. And you can jumper it so you can power it from the rest of the computer. I like to give it a separate supply, that way you can shut off the retro computer without having to shut off the Raspberry Pi. This here will be removed, these shunt blocks, from the future revision of the board. They were so I could put resistors in there just for safety purposes so we don't fry anything. But once you get it debugged, you don't need resistors anymore. So these are just straight shunted across. Ignore them. Then we have various buffers as well as a pair of MCP 23017 chips. Relatively straightforward build.
Next, we have a speech synthesizer board. So a lot of this is straight out of the data sheet. So I came up with two options, one using the SPO256A-AL2, the other using the Votrax SC01A. This chip here, the SPO256, relatively easy to get. You can find them on eBay. Do watch out for counterfeits. I've done videos on counterfeit chips. They do show up all the time, particularly from China. Anyway, relatively cheap. SC01A, you're going to spend like almost $300 for one of these. Kind of hard to find. Maybe you can find a deal, but even then, sometimes they're few and far between. So let's go with the SPO256A-AL2 first. It's hooked up to the data bus. It gets its phoneme, so it is a phonetic speech synthesizer, so it has like 64 phonemes or so that it understands. Gets those from the data bus. There is I think it's this one here, this ALD. You pulse that line, loads those phonemes, it speaks them. When it's done, it will assert this LRQ. So you've got kind of a polling thing you can do. You wait for this to go live, then you load your phonemes, talks a while. This will go live again, you load the next phoneme. Runs off of 5 volts, that's kind of nice. It does have its own crystal, 3.12 megahertz, a little bit hard to find, but you can find them. A little bit of a filter here comes out. I'm working on redesigning the filter, so I'm going to be doing a follow-on that'll have better sound quality with a better filter. Comes out of there, goes down here into a volume control, and up here into an LM386 audio amplifier and out a speaker jack. Relatively simple, straightforward. Now we do need some address decoding, so there is yet another PLD, an ATF16V8, that just looks at the address lines and turns on the appropriate strobes at the appropriate times. And then we also need some feedback. So I have a 74 HCT245 buffer that when you do a read, it will take the result of this LRQ and SBY for standby. It takes those and it puts them on the data bus so that you can pull this thing and see when it's ready to go. And then we also have the Votrax SC01A. Now, I am super protective of my Votrax because they are hard to come by and they are expensive, so there is a buffer sitting in front of it. Buffers the data lines. Loading the phonemes is kind of similar to how the SPO256 worked. You put your phonemes out here on these bits, and then you pulse, maybe it's the STB. Yeah, it's probably the STB here. It's been a little while since I've done a Votrax, but you pulse this, it'll load the phonemes. But the annoying thing about the Votrax is it has two inflection pins, and those are not stored when you pulse the strobe line. You actually have to store those yourself. So that's where the latch comes in handy. The latch goes in here to these transistors, and they're also supposed to be run off 12 volts instead of logic levels. It's run off 12 volts. It's kind of annoying. So yeah, you have to latch the inflection bits, use transistor drivers, you drive your Votrax. And then out of it comes, another filter and into the volume pot. There's also a pitch control pot. Now, if you're building this, only populate one of these at a time. Don't try to put both of them on there. It might actually work, but again, super expensive chip. Take no chances with it. Votrax, another annoying thing about it is it requires 12 volts, so we've got a separate 12 volt supply down here with fuse because, again, I'm very protective of my SCO1A, and a diode in here that is a transient voltage suppressor because, again, very protective of the super rare chip. That is the speech board.
Here we have the speech synthesizer board, currently populated with an SPO256A-AL2 speech synthesizer chip. Things are relatively popular. You can even sometimes still find them in the original Radio Shack packaging. Sometimes not. Anyway, you can get those. There's a footprint here for Votrax SCO1, much harder to find and vastly more expensive, but I think it sounds better. Then we've got associated buffers and ATF 16V8 I/O decoder. We've got the crystal that goes with that, SPO256, and we've got its audio amplifier. There's spots for a couple jacks, one of them for line out and one for amplified speaker out. Potentiometer for volume, another potentiometer for pitch for your Votrax. So what do you do when you have 5 boards you want to do and your Clover computer only supports 4 boards? Well, of course, you make a 5-leaf main board. So this one is a pentagon. It's a little bit bigger than the one that was a square, but you can see we've now got 5 boards mounted on here.
Okay, let's do another demo now that we've got a lot more things working. So let's reboot it. As usual, it boots into the machine code monitor. We hit B to boot. But now we have all kinds of devices. We have a ROM disk as before and a RAM disk just like before. But now we've got a floppy disk. We've got Super Disk, which is a disk that is emulated by my Raspberry Pi Supervisor. And we've got 4 CompactFlash devices. So let's take a look at these. A colon, that is the flash ROM drive. B colon, RAM disk, it has nothing on it. C colon, this will be a 1.4 megabyte floppy. As with all floppies, it's kind of slow and clunky. See, I've kind of copied the same thing to most of these. I only have so much stuff. D is my super drive that's served by a Raspberry Pi, so I can do simultaneous software writes and use a shared file system. It is not there. Let me restart it. Let's try that again. There we go. So that's the super drive working. It has all of my software development stuff on it. And then E is a CompactFlash. F is another CompactFlash. G, you can ignore these files. They say things like disk B and C, but that's because they were originally intended to be drives A through D. But those are the CompactFlash. And if we run stat, you can see all of these, from the first one being the ROM disk, then the RAM disk, the floppy, and the super drive, and then the 4 compact flashes. So let's take a look at some of the software. I put some stuff here in the ROM image. So first of all, I have Tiny Basic. So this came from a Tiny Basic for the Arduino that I found online. And I managed to recompile it to run on CPM 8000 because what good is Retro Computer if you can't demonstrate it using BASIC? There we go. Tiny Basic. 10 print. Scott was here. 20 go to 10. Run. Alrighty. And then we can cancel back out. So you can actually run non-trivial basic programs. I've got the Tiny Basic, so it supports things like writing to ports. That's how I did the little demo where the display was incrementing on the display board. What else do we have here? One of my friends over at Vintage Computer Forum found me a maze generator. That was Chuck G. Found it from one of his old BSD tapes. If I run maze, look at that. We can generate a random maze. And what else is on here? Well, I also found a Zork called Mojo Zork. Now, all of the Zork, the Infocom games, they use something called a Z machine, which is kind of like a virtual machine, kind of like a bytecode machine. And if you implement a Z machine, you can play any Z machine game. So if we run Zork, it ought to load up Zork 1. Again, I had to modify it a bit, get it to compile on here, get it to fit in memory. Open mailbox, take leaflet. But any proper vintage computer needs to be able to run Zork, doesn't it? Let's see if we can get ourselves killed. South, east, open window, enter window, west, take lantern, turn on lantern. I know enough Zork, I can do some of it by memory. Move the rug. Open trap door. Down. North. Will we find a troll? There he is. Let's look troll. Talk to troll. Punch troll. Hit troll. I don't have the bloody axe. Yeah. Look. Let's see if I just do this enough time. Oh, there we go. I have died. I screwed around too long, and the troll killed me. Perfect. That's what I wanted to show. Look at that. We got 25 points. And we did that by standing around looking at a troll until it killed us. Wow. Let's go over to SuperDrive on Drive D. Now, someone over on Hackaday, because this project made Hackaday, someone over at Hackaday said that, it doesn't count unless it can run Leather Goddesses of Phobos, an old Infocom game. But the nice thing about Z Machine is you can run just about any Infocom game. So let's load it up. There we go. Blah blah blah. Hit return. I've never played this game. I say I only know about it because someone on Hackaday said it needs to be able to play this. Doors marked ladies. Northeast and northwest. You feel an urge. Northeast. Ladies' room. Take stool. Oh, use toilet. Sure, it's that kind of game, is it? Southwest, northwest. Yeah. So we can't go in the men's room because I think we have declared ourselves as female by going into the ladies' room. Stool, a flashlight, a comic book. Blah blah blah. I don't know. Can I go anywhere? Oh, I have been captured. Okay. So yeah, I mean, like I say, any Infocom game you want to play, you can pretty much play it. Let's see what else is sitting around here. I've made a few other things. So if you're an RC 2014 person, you're probably very familiar with ClearDir. I couldn't find the source for ClearDir, so I just wrote it myself, and we can initialize our directory. So there, I initialized the RAM disk. What else is there on here? Oh, there is an LED on the board. I don't have the camera pointed at the board, so you can't see it, but I wrote LED on and LED off. We'll turn the LED on and off. Oh yeah, and of course, since we couldn't get Ed to work last time, let's load Ed just to prove we fixed that bug. Foo.text. Insert. This is a test. There we go. And we wrote that to the RAM disk. Type B::foo.text. There we go.
Okay, I did promise a speech synthesizer demo, so I have the speech synthesizer board hooked up here, hooked up to a little speaker sitting back over there. Let's go ahead and see what we've got here. I wrote a program called Say. It used a text-to-speech library called Retro TTS, which I think was written in Python. I converted it to C, and we can make it say things. Text-to-speech is not perfect, so let's see how it does.
Hello, YouTube.
I think it did say hello YouTube just fine. This is the Zilog Z8000 retro computer speaking to you.
This is the Zilog Z8000 retro computer speaking to you.
So yeah, the text-to-speech makes it really convenient. This is a phoneme-based speech synthesizer, so you can see it did translate the words into the phonemes. Sometimes it gets them more right than others. What else can we make it to say? Do you want to play a game?
Do you want to play a game?
Working as expected.
Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.